Well, the last two videos that we just had talked about the fact that when we look at stars in the night sky, they vary in color or surface temperature, and they vary in brightness. And in doing that, we showed that we could talk about different methods of measuring temperature of the surface of stars. And we also talked about two magnitude scales that we can show how stars' brightness can be given by magnitude. So on Earth, we know that the rules of physics shows that there's a relationship to temperature and brightness, and we can see that. So the question is this relationship, does this relationship hold on Earth, and does it hold in for stars and all of space, or are there other rules that we don't know anything about? So how would you test this? Well, two astronomers came up with one way to do this, and they did it separately. One was a European, Northern European. Another one was an American. And so Hartsprung and Russell came up with a means. And what they did is that they made a graph. And on this axis down here, they graph the temperature of the surface of stars. And on here, the brightness of stars. And the scales on this is such that it gets brighter going up. So it goes brighter going up that scale, dimmer down, and it gets hotter going to the left and cooler going to the right. And what you would do with this scale or with this graph is they would look at a star and they might determine its brightness. So that's the brightness of the star. And they would determine the temperature of the star. Anywhere along that horizontal line would be the same temperature of the star, the same brightness of the star. Anywhere along this vertical line would be the same temperature of the star. And where they cross, we put a data point. And then you do this for star after star after star. So if they had gotten this by plotting data points for many stars on what we call the H.R. Hartsprung and H.R. Russell diagram, the H.R. diagram is what we call this. If they had plotted data for many, many stars, and this is what they got. So they plot a data point. Each one of these data points represents the brightness and temperature of a particular star. And so if they had plotted this for a group of stars and got something like this, mathematically we know what this means. It means that brightness and temperature are random. There's no relationship here. In which case, there could be unicorns out there, meaning magic. Or in other words, other rules and what we know of as far as how nature works and what we see for Earth. See, what we want to see if we could find a graph that looks like this. We're kind of all seen this before. You have X and Y, and you have a line. And so what we say is that whatever value you have for Y depends upon what is your X value. Really what we're saying is that Y, should call f of X, is somehow related to X. Whatever's on the vertical depends upon what's on the horizontal axis. And the straight line shows that. That's random. There's no relationship. What we're showing is that for any Y value, there's only one X value that gives that value, which means that Y is a function of X. You probably remember this from math because you loved it so much. And it's wonderful. But that's not that. And so then we'd really question what the rules are about the universe. But luckily, what happened is they did not discover that, but rather what they discovered is that data points basically fell within a very narrow region. Each one of these dots represents a data point for one star that we had plotted on this. And what that says is that, yes, there's a relationship between what's on this axis to what's on that axis. It's not just random. That's what that is. It's random. It's not random. It's not simple, like a straight line perhaps, but it's not random. Sorry. No unicorns, guys. There are rules of physics that we can understand how the universe works. And so this graph here, the HR diagram, turns out to be one of the most important diagrams that we'll use a lot for the remainder of the semester. So let's look at this. Let's get an idea. So this area right here, where most of the stars end up, is known as the main sequence of stars. Just a fancy name. That stars along that axis, that little area that we call main sequence, those stars are just normal stars. And what that means is that these stars, let me go ahead and erase this area right here, that main sequence, I'll put main sequence as MS, main sequence stars are just normal stars. And when I say normal stars, I mean basically that they are producing energy by the proton-proton chain of some form, which we talked about before in the last unit. So they're just normal stars. If we look, the sun is right in the middle, so our sun's kind of an average star here. So if I ask you on the main sequence, what matters? First off, what matters is, as I said, how the energy is formed. And it turns out that stars spend most of their lives on the main sequence. There's only 2 times when a star is not on the main sequence. When the star is in the process of being birthed or being born, or when a star is dying. And we'll see what's going on for birthing in this unit and then dying in next unit. They won't be on the main sequence. But generally, if I ask you, where do stars spend most of their lives? They spend their lives on the main sequence. They're just normal stars. And it turns out where they are on the main sequence depends upon their mass. And it turns out for stars, the most important property of any star is their mass. Most important property. Is that. So let's look at this main sequence a little closer. And so what we find up here at the very top is that they're very bright and they're very hot. So these stars are known as the blue giants. That's their names. They're big, they're hot, and they're very bright. Another thing is they don't live long, short lives. Short lives. And when I say short lives, what I mean by that, I mean that maybe tens of millions of years. It's a long time for you and me, but not for stars. Those stars are so bright, it turns out that when we look into the heavens, that's what we see primarily. But are they the most common stars? Well, we'll find out in just a moment. Now, when I look at the bottom of this, what I've got down here, these stars are small stars. They're very cool and they're very dim. These are known as the red dwarfs. The red dwarfs. These are small. They are cool. And they are dim stars. And even though they're a lot smaller than the blue giants, yet these guys will live a long time. These guys can live more than 1,000 billion years, meaning over 1 trillion years. Well, how is that the case? Well, it turns out that for red dwarf stars, they don't use their fuel very quickly. Compared to a blue giant, they just burn through their fuel. You know, for a long time I had 2 cars. One was a old big pickup that I used in the desert lot out in Arizona. And this thing is pretty close to a 20-gallon tank. And if I drove it from LA to Tucson, where I have a house, generally it would take maybe 2 tankfuls to get there. 20-gallon tank. But I also owned a Prius, and that's what I drove mainly from here to Tucson. 10-gallon tank, and it would just about get me all the way to Tucson. 10 gallons versus a lot more gallons for this big car, this truck. And the reason why is that the Prius uses the fuel much more slowly and efficiently than my big truck. And that's how red stars, the red dwarf stars, work compared to the blue giants. Now, in between there is our star. So right in there, I'll put green there. This is where the yellow dwarf stars are. And they're in between both of those. They're not as hot, they're not as big, they're not as bright as the blue stars, but they're bigger and they're hotter and brighter than the red stars. These guys will live for about 10 billion years. So let's think about this. When you look at these things, these stars are down here. The red stars are low mass. At the very top, these stars right here are high mass stars. High mass. So in between, the mass is in between for the yellow dwarfs compared to the red dwarfs and the blue giant stars. So think about this. Put this together. Think it through. If I go up the main sequence, the stars get bigger, the stars get hotter, the stars get shorter lives, and they get brighter. Going down the main sequence, the stars get smaller, they get cooler, they get dimmer, but they get much more long-lived than the blue giants. What a mess. I need a bigger whiteboard, guys. Poor people having to see my stuff. What a mess, huh? So I hope this is clear. Now, what about star populations? Again, when you look at the night sky, what you see, it seems like most of the stars are blue giant stars. So you would think those must be the most common stars in the universe. Is that true? Well, don't believe what you see. I'm going to go ahead and erase this now. So walk through that carefully. Sorry, such a mess. Oh my goodness. It turns out that what you think is the most common star is not the case. If I look at a graph here at numbers of stars and star types, let's say this is the blue giant, the yellow dwarfs, and this here is the red dwarfs right there. It turns out that blue giants are actually very rare. That's strange. Turns out that yellow dwarfs are more common. But the most common stars are the red dwarfs. Why is that the case? Well, think about this. Red dwarfs, they live forever, it seems. They live a long time. Just so you know something, we think that the age of the universe now, the whole shebang is the universe. The age of the universe, we believe, is 13.8 billion years. So what does that mean? What it means is that every red dwarf that's ever been born, well, they're young still. The oldest stars are not much less than 13 or 14 on the billion-year scale, and red dwarfs have lived for 1,000 of those or more. So every red dwarf ever been formed are still around. But there's another thing, and that is, doesn't take a lot of mass to make one of these stars. So these are more probable in being formed. Because see, with the blue giants, what happens is that they only live a short time. So because they only live tens of millions of years, many generations of these stars have come and gone. They die in the most cataclysmic explosion that you can see in nature called a supernova, a type 2 supernova. We'll talk about that next unit. So they don't last that long, and so they don't add up in numbers. They go away. And there's another thing. It takes a lot of mass. So it takes large mass for a blue giant to form. That's less probable than a red dwarf. So when I look at stars that are born, the most probable stars will be the red dwarfs. The least probable stars will be the blue giants. And so the issue here is, why don't we see all those red dwarfs? Well, remember, they're small, so surface area is smaller. They're dim because they're cool. That goes back to Stefan Boltzmann's law and how much the luminosity is, meaning how much light actually shines from this every second for every square meter. Small. It's cool because luminosity is related to temperature of the surface to the fourth power, remember? So they're dim, so we don't see them. If we can jack up their brightness a little bit, the universe will probably be filled with these guys. We would see them, how many there are. Blue giants are rare, but they're so bright that we can see them from very far away. That's why the night sky is filled with them. So the issue here is that we have this relationship of numbers of stars. If I ask you on the exam for Unit 2, which is the most common? Obviously red dwarfs. Why? Doesn't take a whole lot of mass to make them, so they're more common to be formed, and they live forever. None of them have died yet. What's the least common? The blue giants. Why? Because, well, there takes a lot of mass to form them. They die very young. They're not common to make, so they're, generally they don't add up to high numbers. Why do we see them? Because they're so dang bright. When I've talked about yellow dwarfs, they're just in between everything, kind of averaging between the blue giants and the red dwarfs. So where do we go from here? We need to talk about some general features of stars. Then we'll go into the last topic, and that is the birth of stars for this Unit 2. So guys, I hope that this is clear and that is understandable to you. I'm around, I'm grading. That's going to be what I'm going to do the rest of the week. I will not put any more lectures up this week. This is enough for you to go through. Remember to continue working on the study guide 2, answering that. I'm going to put down on next couple of days, I'll put on the Canvas site Chapter 5 questions, and then I'll probably go ahead and just put in Chapter 10 questions at the same time. That way you'll be able to work on both of those and then get them in as you can. I'll get due dates as soon as I can. I hope you guys are doing well, and I will talk with you very soon. I'm watching email. I've got thousands of emails. It's going to take me a while to wade through everything. Go online and look at these videos. Take care, guys. Bye-bye.